Hi students, in the previous session we were discussing about the atomic force microscope. Atomic force microscope is an equipment used to study the surface structure of a nanomaterial. It is, a, it is based on scanning probe microscopy technique. Here, the van der Waals force between the probe tip and the sample is used to determine or image the surface structure of the sample. It can be used in two modes, a contact mode when the metallic tip of the probe slightly touches or lightly touches the surface of the sample, and a repulsive force originates between the tip and the sample, and that is measured to study the surface topology. Whereas in the non-contact mode, the tip does not touch the sample and there's an attractive force between the cantilever and the cantilever tip and the sample, which is used to measure the surface structure. Now this is the diagram of an AFM. Now this is the sample. Here there's a cantilever with a probe attached to it. A cantilever is a beam which is fixed at one end and free at the other end. As the raster scan drags the cantilever over the surface, this metallic tip moves over the surface and there will be a force between the tip and the surface of our sample, which will give us an idea about how the surface structure of the sample is. Now, as this AFM cantilever moves over the surface, the cantilever undergoes vertical deflection. And to measure this vertical deflection of the cantilever, an optical lever is used. That is, a laser optical lever means something based on light. A laser beam is allowed to fall on the cantilever, and depending on the deflections of the AFM cantilever, the laser beam will be reflected at different angles, and it is collected by a position sensitive photodiode, which will in turn send the signal to the detector. And even a very small deflection in the cantilever is obtained as a magnified deflection or a magnified output in the detector. So the AFM resolution of the AFM is, or an excellent resolution is achieved, the AFM, as low as 10 picometer, and they can image samples both in water and air. And AFM has a number of refinements that enables it to attain this excellent resolution or atomic scale resolution. One is the laser beam which is used, or the optical lever which is used for the sensitive detection of the cantilever deflection. This we discussed in the last session. And the second refinement which is used so that the AFM attains a good resolution is the nature of the AFM cantilevers, that is, very small AFM cantilevers having low mass is used. Okay. Now, the third refinement which helps the AFM to attain a good resolution is related to the AFM tip. Now, AFM tips are manufactured by a number of microlithographic techniques because the tip is very, very small. And AFM tips are actually rounded so that their end radius can be determined. So they are rounded at the end. They are not exactly pointed. It has a rounded edge. Okay. So that the end radius can be determined. The tip is rounded so that this radius can be determined. Okay, the end radius generally limits the resolution of the AFM. That is, the resolution of the AFM depends on the end radius. So the end radius limits the resolution of the AFM. Now we are discussing about three types of AFM tips. One is the normal tip, which is 3 micrometer tall and pyramidal with end radius of 30 nanometer. Then electron beam deposited tip or it's called a super tip. It is made by pointing this normal tip into an electron beam of a scanning electron microscope. So this tip offers a high aspect ratio. Aspect ratio means length to diameter ratio. It offers a high aspect ratio, that is its length is it is high, it's very long, whereas its end radius or diameter is very small, so that this aspect ratio becomes large, and it has a better end radius than a normal tip. That is, a smaller better end radius means it has a smaller end radius than the normal tip. Then comes the ultra lever tip or ultra tip, that is, it is made by an improved microlithography process, and it offers a moderately high aspect ratio and end radius as low as nearly 10 nanometers. Next, we discuss about the piezoceramic tube on which the sample is placed. You can see in the figure the piezoceramic tube. I hope you remember what we saw in the figure, how our piezoceramic tube is. This is the tube on which the sample is placed. Now the purpose of this piezoceramic tube is to provide dynamic scanning motions. That is, a ceramic tube will expand and contract, or it will move, so that it allows dynamic scanning movement or scanning motions. So let's see how. So I think you all might be knowing what are piezoceramics. So piezoceramics are materials which expand or contract when subjected to a voltage gradient. That is, if a bias is given across two of its faces. Okay, suppose you have a piezoceramic sample. So that you apply a bias here. Along these two faces, you are applying a positive and negative potential, so that the other two faces will undergo mechanical vibrations, or it will contract or expand these two faces. And the corollary is also true. That is, for a piezoceramic material, if you expand or contract these faces, then a voltage gradient will be developed. Or if you set the piezoceramic crystal into material into mechanical vibrations, then a voltage gradient is obtained. So what you do here is, in the AFM, you use a tube shaped piezoceramic, or you have a piezoceramic tube, because it is a one piece construction with high stability and large scan range. Now 4 electrodes cover the outer surface of the tube, while a single electrode covers the inner surface. On applying the voltages to one or more electrodes, what will happen to the tube? It will bend or stretch, moving the sample in 3 dimensions. This is what I told. The tube will bend or stretch itself, and the sample is placed on this tube. So what will happen? The sample also will move together with the tube, and an excellent scanning of the surface of the sample can take place. Okay, so the tube piezoceramics position the tip or the sample with high resolution. So let's discuss once again what piezoceramics. These are a class of materials that expand or contract when subjected to a voltage gradient, or they create a voltage gradient when forced to expand or contract. AFMs use a piezoceramic tube, which is a one piece construction with high stability and large scan range. 4 electrodes cover the outer surface of the tube, while a single electrode covers the inner surface. On applying voltage to one or more electrodes, what will happen to the tube? It will expand or contract, or it will bend or stretch, moving the sample in 3 dimensions, allowing a dynamic scanning possibility, okay, of the sample. So this much about piezoceramics. So we have discussed in our previous session and this session about what is an AFM, Then how does it work in the contact mode and non-contact mode? Then what are the refinements which allow it to have an excellent resolution? First is the optical lever or laser beam deflection. Then what kind of AFM cantilevers you use? What kind of AFM tips do you use so that you attain the best resolution? And how is your piezoceramic tube? Okay, um, which allows the AFM to have a dynamic scanning of the sample. I hope this session is clear to all of you. If you have any doubts, please do contact. Thank you.